So today we're looking at some more optical phenomena that we get from refraction and reflection with cool applications of the world around you. First, we'll talk a little bit about dispersion. And when you guys did the lab, you got to see a little bit of this by taking a white light, shining it through some plastic, and having it refract. If you shine it through a prism, you can see the entire spectrum of color from red to yellow to green to blue to purple. We learned through the lab that the index of refraction is different for the different wavelengths of light. Newton actually really got interested in this study, and he pioneered the study of dispersion. And he said that the light particles, because remember he believed in the particle theory of light, the different particles would slow down when they would hit the more optically dense medium. So in the case of light, we'd say that blue slows down more when going through a refractive medium, like glass or plastic, more than red does. So it slows down more, it bends more. This is just a little web link that shows you a moving demo of the waves as they are going through the medium and how they are dispersed by refracting with greater indices of refraction. So the blue bending more, again, than the red does. One of the other optical things we learned about in our lab was that if you get to a certain angle beyond what we call the critical angle, then all light, when it goes from a more optically dense medium to a less optically dense medium, the light will, all the light will in fact reflect, and none of it will refract. So we've got to learn and understand more about what this critical angle is. And when you hit the critical angle, you go beyond it, you can get total internal reflection. It's important to note that it's only going to happen when you go from more optically dense medium to a less optically dense. So if you look at the different angles as you're approaching from a more optically dense, so we have inside water to outside to the air, the first angle A, you see that as the light comes through, part of it is going to refract. In other words, part of it is going to go right through, come out the other end and refract, and then part is going to reflect. And that's going to be true in any case when you're going across a boundary from a more dense to less dense. Part of it will go through and part of it will reflect. But we see as this angle, the angle of incidence, gets larger and larger, you continue to have the refraction, you continue to have the reflection, but then at some point the angles are going to get so large that as the angle comes in, and here's your angle of incidence again, the angle of refraction becomes 90 degrees. And when it becomes 90 degrees, part of the ray, at exactly that angle, part of the ray will refract off perpendicular to the normal, or parallel to the surface, and part will reflect, but then anything beyond that angle is going to completely internally reflect, so that no light will get out once you get beyond that critical angle. If you're looking to find the critical angle of a material, then you just need to know the indices of refraction, and you kind of figure that out hopefully when you were working on your lab, that when you found the angle where all of the light bounced back, so right here, that angle is going to lead you to, that is the critical angle, and that critical angle is related to the indices of refraction, where this is N1 and this is N2. Keep in mind that this fraction, N2 over N1, better be less than 1, right? Because you can't take the sine of an angle unless it's like 0.75 or something like that. So you take the sine of an angle, that's going to be, the angle has to be less than, the sine of the angle has to be less than 1. So therefore, the ratio of these two guys, and so this is usually like around 1, and this might be around 1.5. And so you can take the sine of that ratio, and you can figure out the angle that is the critical angle. Any light going beyond that angle is going to completely internally reflect. And that was my dog signaling the bell that he wanted to go out. 1 second. Okay, so there's many applications of total internal reflection. You can actually use a prism, which is made of glass or plastic, to reflect light, and it's actually more efficient than even mirrors. So you'll have, with total internal reflection, all of the light that comes in is going to be reflected and bounced back. So if you want to redirect a light beam, then you can use prisms to do it, and not mirrors, and you can get all of the light to be transmitted. Diamond, remember, was a really high index of refraction, n equals 2.24. that gives it a critical angle of 24.6 degrees. So any angle of light that comes in that is greater than 24.6 degrees is going to be completely reflected. And that's most angles, right? Because 24.6 is a very small angle. So any angle that comes in greater than that is going to be completely internally reflected. And that's why diamonds are cut with these cool angles, so that light will come in and it will get trapped inside the diamond. It will bounce around and seem to sparkle. So it takes, the light comes in, it bounces around, and then as it comes back out into our eyes, it tends to sparkle. Also, the different white light will come in, and as you can see from this little diagram, the red light will be refracted differently than the blue light, and so you tend to get these beautiful colors in terms of the blues and reds kind of sparkling from the diamond, and that's because of the different refractive indices for the different colors of light. And no, I don't know anything about diamonds and why some are more valuable than others if they have different colors, so I don't know that stuff. Okay, fiber optics, also super cool application of total internal reflection. The idea is you have a light pipe. This is maybe something made out of glass or plastic, and it can bend around corners, and it has some thickness to it, but it has the thickness such that if you shine a beam of light, like this red beam right here, if you shine a beam of light, no matter what angle you shine that beam, the angle of incidence is going to be greater than the critical angle, and so the light is going to completely internally reflect and bounce off. And so you can take these light pulses, and they can come through, and they will just continually bounce off the edges of the glass. Typically, it's fiber optic is often glass or plastic, and the light will bounce and totally internally reflect, and then basically you'll get out the other end what you put in one end. So it's very, very efficient in maintaining the energy from these light. None of the light that goes in actually ever escapes. This is a little photograph of a demo with a laser shining into it looks like a piece of plastic, so a long piece of plastic here, and then you shine the light in, and whatever comes in is going to be internally reflected, and so it will travel through and come out the other end. So we do some really neat demos in class for those of you who missed the ones in class. That's another little kind of artistic version of fiber optics, light coming in one end and then going straight through and bouncing and coming out the other end. There's lots of neat medical applications for fiber optics. Really non-invasive surgeries now with this sort of arthroscopic technique where you puncture a little hole, and instead of having a massive slice, oh goodness, hang on. Okay, back to it. So we have these really small, intricate medical devices now where we can get inside the body and with cameras be able to see what's going on with these small arthroscopic equipment. You can do microsurgery. So great advances in medicine by using this sort of fiber optic technology. Okay, let's talk about rainbows. This is kind of a neat picture because you can actually see the double rainbow. And if you look closely, because we're going to talk about what's happening here. The bottom rainbow has blue at the bottom and then red, orange, yellow, red at the top. And then the double rainbow that you see up above, it looks like it's flipped. You see how it's blue above and the red down below? We'll talk about why that is in just a second. So rainbows are the combination of three cool optical effects, namely refraction. As light is going to go into a little droplet of water, it's going to refract or bend, and then it's going to reflect off the back of the rain droplet, and then because the indices of refraction for blue is different than red, it's going to bend different for different colors, so you have some dispersion. So let's look closely at what exactly is happening. So you have sunlight coming in, so sunlight comes in right about here, and then as the white light comes into the raindrop, we are estimated with a spherical droplet, the light comes in and it immediately refracts, so it bends a little bit. And the red doesn't bend as much as the blue. The blue bends more. So they disperse a little bit right there. But then they get to the back of the raindrop and they bounce off with total internal reflection. And then the rays come out to another boundary between the water and the air, and they refract again, so they bend again. But the disparity between the red and the blue, every time they refract, it gets to be greater. So once they bounce out, you get the red coming out down below, and then you have the blue coming out up above. And so you get dispersion effect from the little rain droplets. So light that's coming in will bounce off the raindrop. It will totally internally reflect, and it will disperse and then come back out again. And when you see, and these angles are interesting too. So the angle between the sunlight and the violet light is 40 degrees, and then 42 degrees is the angle from the sunlight to the red. So those angles can be important when you start paying attention to what's going on. So blue bends your most. You're going to have a total angle of 40 degrees, and red bends the least, so you're going to have a total angle of 42 degrees. Think of it as mostly reflected and not so much being bent. Okay, so what happens then when you're viewing raindrops? So if you're standing over here, okay, here's your line of sight. The sun is over here somewhere bringing light rays in. So the light rays come in parallel. You have rain droplets in the air, maybe not where you are, but where the rain is coming down over here. And then as the light hits the rain droplet, it refracts, it reflects, and it comes back out. It bends out. And it bends out at an angle, depending on where the drop is, 40 degrees for blue and 42 degrees for red. And so you get to see this beautiful rainbow. And what you see is the red on the top and then the blue down below. So you take that angle, that 42-degree angle, and then you spread it, in each direction. You're going to get that cool effect. That's just because your eyeball is here, and so if someone's over here looking at it, if their eyeball's over here, they're going to see slightly different angles, but they can still observe the rainbow. But you're going to have the entire 180 degrees. If you happen to be like in the airplane, you could actually see a full 360-degree rainbow. It's just because of the horizon we only see half of it. But yeah, you could see that cool effect if you were in an airplane seeing sunlight going through some rain droplets. Now, double rainbow is the one that bends twice. So here's the idea. You have the sunlight coming in from here. It comes in, it refracts, it reflects off the back once, and then it reflects off the back twice, and then it comes out and refracts and it disperses even more. So that angle you're going to see up higher, the double rainbow is like a 50 to 53-degree angle, and you don't always get to see those. They're dimmer because every time you have a reflection, some of the light is going to be going through and some of it's going to be refracting. So you do lose a little bit of light with the different reflections. Okay. And that is my last slide.